At 8:45 on January 27, 1986, engineers responsible for Challenger's rocket boosters joined a conference call. The forecast was dangerously cold. No shuttle had launched with these seals below 53 degrees Fahrenheit. Their recommendation was clear: do not launch. NASA officials questioned the evidence. Thiokol requested a 5-minute private caucus. It lasted 30. Engineers still objected, but when the call resumed, management's answer had changed: launch. The next morning, 7 people boarded Challenger. One was schoolteacher Krista McAuliffe. At 11:38, the shuttle lifted off. Less than 1 second after ignition, a camera recorded black smoke escaping from the same booster joint the engineers had feared. For the next 72 seconds, Challenger climbed. Then it broke apart live. The disaster is remembered for what happened in the sky. But the harder question began the night before. How did do not launch become launch in 30 minutes? Challenger's flight was officially designated STS-51L. On paper, it was the 25th mission of the Space Shuttle program and Challenger's 10th journey into space. But to the public, this mission was different. Francis Dick Scobie commanded the crew. Michael Smith was the pilot. Judith Resnick, Ronald McNair, and Ellison Onizuka were mission specialists. Gregory Jarvis was an engineer from Hughes Aircraft. The 7th crew member was not a career astronaut. Krista McAuliffe taught social studies at Concord High School in New Hampshire. She had been selected from more than 11,000 applicants for NASA's Teacher in Space project. From orbit, she planned to teach 2 televised lessons, turning a spacecraft into a classroom for students across the country. Her presence placed Challenger in schools and living rooms long before launch day. Students followed her training. Television crews traveled to Florida. At Concord High School, teachers and pupils gathered to watch. The mission itself was planned to last nearly a week. The crew would deploy a communication satellite, release and later retrieve a spacecraft that would observe Halley's Comet and conduct a series of experiments. Nothing about the flight plan suggested that history would remember only its first 73 seconds. The astronauts were fully trained and certified. They had practiced ascent failures in simulators and repeated the procedures until responses became automatic. Yet, the danger that would destroy Challenger was not inside their cockpit checklist. It was hidden in a joint near the bottom of the right rocket booster, and by January 1986, it was no longer an unknown danger. The Space Shuttle had first flown less than 5 years earlier. It was unlike the expendable rockets that came before it. The orbiter returned to Earth and flew again. Its 2 solid rocket boosters were recovered from the ocean, taken apart, refurbished, and reused. NASA presented the system as a path toward routine and economical access to space. The word routine mattered. After the early test flights, NASA accelerated the schedule. 9 shuttle missions flew in 1985. 15 were planned for 1986. One projection called for 24 flights a year by 1990, but the machinery, people, training facilities, and supply system were already being stretched. The later investigation concluded that even 2 launches a month was overambitious with the resources available. Challenger itself had already been delayed. Its original January 22nd date moved as the previous mission slipped. Weather forced another postponement. On January 27th, a problem with an exterior hatch handle consumed more than an hour. By the time it was solved, crosswinds were too strong, and the launch was canceled again. None of those delays caused the accident, but they reveal the environment around the decision. A complex program trying to make an extraordinary machine operate on an increasingly ordinary schedule. Success reinforced that confidence. Every shuttle flight returned with new data, new damage, and new anomalies. When an anomaly did not destroy a vehicle, engineers studied it. Managers accepted a rationale, and the next mission flew. Over time, the boundary between "it survived" and "it is safe" could become difficult to see. Inside Challenger's boosters, a small rubber seal would expose that difference. Each solid rocket booster was taller than a 14-story building and produced millions of pounds of thrust. It could not be manufactured and transported as one continuous tube. Instead, the booster was built in large steel segments, then joined together at the launch site. At each field joint, the lower segment ended in a metal fork called a clevis. The upper segment had a narrow metal tongue called a tang. The tang fitted into the clevis, pins locked the pieces together, and two rubber O-rings circled the booster to keep burning gas inside. The idea sounds simple. If the first O-ring leaked, the second should provide a backup. But ignition changed the shape of the joint. As pressure rose inside the booster, the steel casing expanded. The joint walls moved slightly apart in a motion engineers called joint rotation. The gap was small, but the seal had only fractions of a second to move with it. For an O-ring to work, it had to remain flexible. Pressure had to push the rubber across the opening before hot gas found a path through. Cold made that response slower. A warm O-ring compressed and recovered quickly. A very cold one could remain flattened just as the joint opened around it. If the seal arrived late, gas hotter than 2,000 degrees Celsius could pass through the gap, burning or eroding the rubber. The secondary O-ring was not a perfect independent backup. Once the joint rotated, it could also lose the position required to seal. This meant the booster depended on a component that behaved differently with temperature. Inside a joint whose movement was not fully understood when the system was certified. And previous flights had already left physical evidence of what could happen. After earlier shuttle missions, technicians found O-rings marked by heat. Some showed erosion, others showed soot that had traveled past the primary seal, a sign known as blow-by. The booster had still completed its burn. The shuttle had still reached orbit. The damaged hardware returned as evidence of a failure that had stopped just short of becoming a disaster. One flight became especially important. In January 1985, Shuttle Mission 51C launched in the coldest conditions yet experienced by the relevant booster joints, approximately 53 degrees Fahrenheit. Its O-rings suffered the most severe blow by then observed. Roger Boisjoli, an engineer at Morton Thiokol, the company that built the boosters, studied the damage. He and other engineers became increasingly concerned that low temperature delayed the seals. The concern was not hidden in hindsight. During 1985, engineers argued that the joint required redesign. Boisjoli warned internally that if the problem was not corrected, a joint could fail and place a flight, its crew, and the launch pad at risk. NASA and Thiokol continued to study the problem, but they also continued to fly. Because previous erosion had remained within calculated limits, it was repeatedly treated as an acceptable flight risk. A launch constraint existed, but it could be waived with an engineering rationale. This produced a dangerous transformation. Evidence that the design was failing did not automatically stop the program. Because the failures had not yet destroyed a shuttle, they became evidence that the system could tolerate damage. The Rogers Commission later described the pattern plainly. NASA and Thiokol accepted increasing risk because they had escaped the consequences before. Then the forecast for January 28th moved far outside the experience used to justify those earlier flights. After Challenger's January 27th launch attempt was canceled, the forecast showed temperatures falling into the low 20s overnight. That triggered calls among engineers and managers in Florida, Alabama, and Utah. At Morton Thiokol, Boisjoli and his colleagues assembled charts from previous missions. The data was incomplete and imperfect, but the pattern worried them. Cold O-rings responded more slowly. and the coldest previous flight had produced serious blow-by. At approximately 8:45 that evening, Thiokol presented its recommendation. Do not launch below 53 degrees Fahrenheit, the lowest temperature supported by previous flight experience. NASA managers challenged the logic. They argued that the data did not prove a precise temperature boundary, and questioned why Thiokol was changing its launch criteria so late. That criticism contained a trap. The engineers could not calculate the exact temperature at which the seal would fail, but uncertainty did not make the colder launch safe. It meant Challenger was entering conditions with no flight evidence showing that the joint would work. Thiokol requested a private caucus expected to last 5 minutes. For roughly half an hour, the company debated its answer. The engineers maintained their opposition. Management focused on the inconclusive data and the expectation that the secondary O-ring would still seal. One manager urged another to remove his engineering hat and put on his management hat. When the conference resumed around 11 o'clock, Thiokol had reversed its position. Its managers signed a recommendation to launch. The engineers who opposed the launch were not asked to sign it, and the senior NASA officials responsible for the final launch decision were never told that Thiokol's first recommendation had been no launch, or that engineers continued to object after management changed it. The decision moved upward. The warning did not. During the night, water froze across Launch Complex 39B. Icicles hung from the service structure. An inspection team went to the pad at 1:35 in the morning, returned at 3, and was sent back again before launch. The concern they were assigned to evaluate was whether ice might break free and damage the shuttle. That was a real hazard. It was also not the hazard discussed during the Thiokol call. The ice was visible. The O-rings were sealed inside steel. By morning, the launch had been delayed to allow more ice to melt. The crew received a weather briefing and heard about conditions on the pad. They were not told that engineers had argued the cold could prevent a booster joint from sealing. At 8:03, the astronaut van arrived at the launch site. By 8:36, all 7 crew members were inside Challenger. The final ice inspection ended at 11:15. During the hold at 9 minutes, each station reported its status. Go. At 11:38, the shuttle's 3 liquid-fueled main engines started. Computers checked their performance. Then the solid rocket boosters ignited. Unlike the main engines, the boosters could not be shut down once burning. For the next 2 minutes, Challenger was committed to their thrust. To the human eye, liftoff appeared normal, but one of the cameras around the pad had a close view of the right booster. At 0.678 seconds after ignition, it recorded dark smoke above the aft field joint. More puffs followed. The evidence of failure existed before Challenger had cleared the tower. No one watching in real time could see it. For the first 3 seconds, cameras recorded smoke escaping from the right booster joint. Then it disappeared. Investigators later concluded that combustion debris may have temporarily sealed the opening. Challenger continued to accelerate, rolled toward the east, and climbed into clear blue sky. At 24 seconds, the main engines began throttling down as planned. The vehicle was approaching the region of maximum aerodynamic pressure, where the force of the air against the accelerating shuttle would reach its peak. At 37 seconds, Challenger encountered a sequence of high-altitude wind changes. Its guidance system responded normally, moving the booster nozzles to keep the vehicle on course. The shuttle appeared healthy. At 58.788 seconds, enhanced film later revealed a small flame at the right booster's aft field joint. Within moments, it became a concentrated plume. The flame struck the external fuel tank and the structure connecting the booster to it. Sensors showed pressure in the right booster beginning to fall compared with the left. At 65 seconds, Mission Control told the crew they were go to throttle up. Commander Scobie answered, "Roger, go at throttle up." It was the final transmission from Challenger. At 73.124 seconds, the external tank's liquid hydrogen section began to fail, Almost simultaneously, the right booster's attachment was compromised. The vehicle was forced out of alignment while traveling at nearly twice the speed of sound. Challenger did not simply detonate like a bomb. The tank failed, propellants were released into a vast fireball, and aerodynamic forces tore the shuttle apart. There had been no cockpit alarm announcing the leak. During booster flight, there was no survivable abort that the crew or mission control could have used to stop what followed. On the ground, the first unmistakable evidence was the live image itself. President Ronald Reagan created a commission to investigate the accident, chaired by former Secretary of State William Rogers. The inquiry examined film frame by frame, telemetry by fractions of a second, recovered wreckage, engineering records, and the decisions made before launch. One commission member was physicist Richard Feynman. During a televised hearing, Feynman took a sample of the O-ring material, compressed it with a clamp, and placed it in a glass of ice water. When he released the clamp, the cold rubber did not immediately return to its original shape. The demonstration did not reproduce the entire booster joint. It made one crucial property visible. At low temperature, the seal lost the rapid resilience its job required. The commission traced the physical failure to the aft field joint of Challenger's right solid rocket motor. Hot gas escaped after the seals failed, eventually damaging the external tank and initiating the vehicle's breakup. But the report did not end with rubber and steel. It found that the launch decision itself was flawed. People making the final decision lacked critical information. Concerns had failed to move through the management structure. Persistent erosion and blow-by had become accepted as normal because earlier missions survived them. The accident therefore had two histories. One began at ignition, when a cold seal failed to close a moving gap. The other began years earlier, each time damage returned from a successful flight and was absorbed into the definition of acceptable. Fixing Challenger's booster joint would be difficult. Fixing the second failure would be harder. The space shuttle did not fly again for 32 months. Engineers redesigned the booster field joint. The new design added a capture feature to limit joint rotation, changed the sealing arrangement, and added heaters to protect the joint from cold. The boosters were subjected to new tests and reviews before being certified again. NASA made more than 200 changes across the shuttle system. Crews began wearing full-pressure launch and entry suits. A limited escape system was added for certain controlled flight situations. Safety oversight and management procedures were reorganized. On September 29, 1988, Discovery launched on STS-26 and returned the shuttle program to flight. But no redesign could change the decision made on January 27, 1986. Challenger's crew were Francis Scobie, Michael Smith, Ellison Onizuka, Judith Resnick, Ronald McNair, Gregory Jarvis, and Krista McAuliffe. They should not be reduced to the final image of a vehicle breaking apart. They were pilots, engineers, scientists, parents, teachers, and explorers who boarded a spacecraft they had been told was ready. The lasting lesson is not that complex machines can fail. Everyone in spaceflight already knew that. It is that repeated success can make a known warning feel less urgent. A system may record damage, investigate it, assign it a category, and continue operating until the day the damage no longer stops inside the accepted limit. The night before Challenger launched, the correct question was not whether engineers could prove the O-rings would fail. It was whether anyone could prove they would work in conditions they had never survived before. For 30 minutes, that distinction disappeared. 73 seconds after launch, it returned. Challenger was not lost because one person ignored one obvious answer. It was lost inside a system where uncertainty moved upward as confidence, while the strongest objections stayed below. That is what makes the story larger than one shuttle, one seal, or one freezing morning. When a warning has appeared before without catastrophe, does experience make the next decision safer? or only make the danger easier to accept. If you want more evidence-led documentaries about the decisions behind events the world remembers, subscribe to Meridian Zero.